Hello guys, hope you all are doing well. So in the continuation of the previous GATE series, we are solving the GATE 1991 question, and today we will complete the 1991 paper. Then we have left with few questions including the questions of 1990 as well as 1991. And those questions were, I will solve them after analyzing the latest trend, what actually the question, right now GATE is asking, whether they are important or not. But I have completed all the important questions which can get asked again by with the same concepts. Okay, so today we have a new question. So without wasting time, we'll go into the questions. So what question is saying? For a reversible exothermic elementary catalytic reaction. Okay, so we have a reaction that is reversible exothermic and elementary. Okay, so we have reversible exothermic reactions just like ammonia, N2 plus 3H2, that gives twice NH3. The problem with the reversible reaction is that after certain extent, when the reactant converted to product to some certain extent, the product again converted to the reactant. That's why we need a optimum temperature and pressure to increase the concentration of product. Okay, that's why we use Le-Chatelier principle in reversible reactions, specifically when the reaction is reversible exothermic. Okay, just like reaction of ammonia. So what the question is saying, find the optimum operating reaction temperature and conversion level is 0.8. We have a rate constant K1 and K2 and maximum level temperature is 300. Okay, so we will get an answer around 300 or below 300 or just above the 300. Let's see. So very first thing, in reversible reaction, after when reactant converted to product, if you will not give optimum temperature and the pressure according to the stoichiometric coefficients, that depends, the pressure of the reaction depends upon the stoichiometric coefficient, whether the moles are decreasing, whether the moles are increasing, whether the moles are same. On the number of moles, the pressure depends, high, low, moderate, and the same way temperature depends on decreasing or increasing the number of moles. So the problem with the reversible reaction, that after some extent they reverse the direction and being converted into the reactant again. So solution, we have to find the optimum operating temperature. Okay, for elementary reactions, rate of the reaction is same as the stoichiometry. We all know that. That is the very first thing in the chemical reaction engineering. So I have written the rate. To understand this rate equation, see, K1 is the rate constant of forward reaction, K2 is the rate constant of the backward reaction. Concentration of A is decreasing with K1. Since decreasing, that's why negative sign comes with K1 and the concentration of A is decreasing. That's why minus K1 Ca. And concentration of Ca increasing with the rate constant K2. That's why I added that K2 Cb, concentration of B, with the concentration of B. So that is the rate of reactions. This is the very first step we require to learn in chemical reaction engineering. Just rearrange this, we will get this. Okay, after putting the value of K2 and K1, I have put the value of K2 and K1. Okay, now Cb, what is Cb? Cb is the Cb naught, initial moles of B into initial concentration of A into conversion, right? But we have Cb naught 0 in the, because we don't have B in the reactant side. We don't have any reactant related to B. We don't have B reactant. We only have A. So Cb not 0. Ca naught we have. Without initial concentration of A, we can't find out how much reaction has completed or the reactant converted to product. Then conversion we have 0.8. Then Ca is the remaining concentration. Ca is the remaining concentration after end of the reaction. So what it will be? Ca naught minus 1 minus Xa. Right? Now, minus Ra is equal to, where is the cursor? Yeah. Minus Ra equal to E, same thing. Cb naught is 0. Ca naught into 0.8. Xa is 0.8. K1, Ca naught into 1 minus 0.8, right? Now, the same thing, 0.8 Ca naught, thus just mathematical things, 0.2, okay? Now, so K2, 0.8 Ca, the same equation there. Now, for optimum temperature, this will be the 0. Differentiation of rate with respect to temperature, not time, with respect to temperature should be 0 for optimum temperature, just like maxima and minima. Okay, so we did that. Okay, after that, just solve, we will get this equation. It's all mathematics. Okay, we will get this equation. This is equal to this. So we will cut the C naught from both the side. Okay, then 0.2 will come from this side, that is 0.8, and these three zeros will be cut with these three zeros. T square will be cut with the t square. This is the sign of multiplication. This is the sign of multiplication. Okay, don't get confused. And 5 3 ja 15. So this 3 into 4 divided 0.2. So it will 0.2 and it will 4. So 4 3 ja 12. So we will get 12 this side and 12 this side and whole thing this side. Taking the log and solving the equation, we will get 307.8. Okay, so which is a little bit higher than 300, but it is optimum temperature according to the the information given in the question. The temperature is 307.8 Kelvin. Okay, so hope you understand this question. Just a concept is here. If you will understand how to write the rate equation and then putting the values and then differentiation, that's all. Then the remaining thing is mathematics. Okay, so going to next question. The rate of a liquid phase reaction of a type, very first thing, it is a liquid phase reaction. That means expansion factor. What is expansion factor? That means EA is equal to 0. Always remember, expansion factors changes in gas phase reaction. For liquid phase reaction, expansion factors always will be 0. Always will be 0. Okay, is found to be independent of the concentration of A and B and equal to the 1 kilomole. That means it is a zero order reaction. Okay, at 300 Kelvin. Find the conversion in a mixed flow reactor having volume equal to 2 meter cube with feed concentration of A and S equal to 5 kilomole per meter cube. We are feeding A and S, okay, along with B, but we don't require S. Okay, we just since A and S has equal concentration, so we just require the concentration. Okay, that's all. So you can neglect S. Okay, feed flow rate is equal to 1 meter cube per minute. That is V naught, small V naught. Reactor temperature is 300 Kelvin. Okay. If the activation energy of the reaction is 83.1 kilojoule per mole, find the volume of an isothermal plug flow reactor for the same conversion feed conditions as in case of the above mentioned reactor, but the temperature is 320. This is very good questions. Okay, so start solution. Applying performance equation of CSTR. So this is the performance equation of CSTR. We all know that. Okay, X naught is the conversion of the reactant which is in the inlet, and all the time it becomes 0. All the time, because there will be no conversion at the starting of the reaction. Conversion always comes after the starting of the reaction. Okay, now putting all the values, okay, we will get this. Meter cube will cancel out, minute will cancel out, kilomole will cancel out, meter cube. and we see that we need value of conversion, and that is unitless, so we will get 0.4. That is first part, that is the conversion in the plug CSTR, continuous state tank reactor. Okay, now this we have solved everything at 300 Kelvin, right? 300 Kelvin. But the question is saying what will be the volume of reactor of plug flow reactor 320 Kelvin. That means the rate constant, this value, because rate constant is the function of temperature only. At 300 Kelvin, the rate constant is 1. So we have to calculate the rate constant at 320 Kelvin in order to use in the performance equation of plug flow reactor, which is at 320 Kelvin, right? So if the activation energy given as this, volume of isothermal plug flow reactor for the same conversion 0.4 that we have calculated right here. Okay. And feed condition as in the case of the above mentioned reactor, but the reaction temperature is 320. Where is the cursor? 320, right? So okay, so we have to calculate the rate constant at 320 because rate constant is only the function of temperature, and temperature is right now for plug flow reactor is 320. So applying Arrhenius equation, this is Arrhenius equation, we all know that. Okay, putting all the values, I just put all the values and I'll get K2 is equal to itna kilomole per meter cube minute. We will not forget the unit for a single second. Unit is very important in order to score high in the gate. Applying the performance equation of PFR. This is the performance equation of PFR, right? Putting all the values. One thing here is an important thing for zero order reaction. For zero order reaction, write it down in your copy. For zero order reaction, performance equation of PFR and CSTR is equal to same. If you will solve this integral, you will get x1 upon Ra because CA0 is constant. You will get x1 upon Ra. Okay, so this is the same as the performance equation of the CSTR. So for zero order reaction, performance equation of PFR, batch reactor and CSTR is almost equal to same. Okay, for liquid phase reaction, remember for liquid phase reaction. Okay, now I just put all the value. Okay, I'm getting volume equal to, just solving for the V, put all the values, solving for the V, volume is equal to 0.249 meter cube. Okay, so hope you understand this question. These two questions are very easy, just based on some concept, basic knowledge of chemical reaction engineering. Okay, so moving to the next question. Find the minimum value of K such that a closed loop system having following characteristic equation is stable. So we know that for a system, for a closed loop system having a following characteristic equation is stable when the first row of Raoult theorem will be non-zero or non-negative, right? Will be non-zero or non-negative. Okay, so okay, applying Raoult theorem criteria. So this is Raoult theorem, we know. So in Raoult theorem, what we did in matrix, what we did, we all know that in matrix we go from here, this into this minus this into this. But in Raoult theorem we go from this into this minus this into this. So suppose we get after multiplying k into k plus 1 minus 4 divided by k, we will get value A. So what is A? A is this, k into k plus 1 minus 4 divided by k. This is Raoult theorem. If you, okay, so again how 4 will come here? A into 4 minus 0 into k, that will be 0 divided by A. So that is Raoult theorem. Okay, just learn for particular Raoult theorem criteria. There is a book called DC Sidkar, DC SI Sidkar, DC Sidkar. So that book is very important. Okay. And for process control, that book is very helpful, but it contains certain mistakes. So just be careful when you are going through it. that will, you can find this book on khannapublishers.in. okay, just google khannapublishers.in. you will get all the book which is published by the Khanna publications, and some of the books are very important regarding chemical engineering. Okay, so solving this equation, we will get k is equal to 1.5, neglecting the negative value, because in the first row of the route array, the value should be non-negative and non-zero in order for a stable system. For a stable system, the value in the first row of the route array will be non-zero and non-negative. Okay, so k will be greater than 1.5 or equal to 1.56 in order to maintain the system stable. Okay. So ending up 1991 solution, few questions are left which I will cover after analyzing the latest trend of the GATE exam, whether they are important or not, because some mistakes are also there in the questions. Okay, and the reason, so we will see that question, but I'll promise you that not a single question I will skip from the solutions of 1990s. Okay, from 1990 to 2000 we will solve each and every subjective questions, and after that from 2000 we will see objective questions, and hopefully if we will, at the end we will get time, we will see mechanical questions as well as engineering science questions of fluid mechanics, thermodynamics and heat transfer. Okay, so bye guys, take care.